Hey everybody, Mrs. Mancuso here, and today we are doing our Unit 6 review. So I just want to remind you, Unit 6 began with us coming to the understanding of a new subatomic particle, the first subatomic particle. So something within an atom. The first thing realized was an electron. And so remember, we did the sticky tape lab and we saw the transfer of electrons, and we saw that positive negative interaction, and we also saw that when two things have the same charge they repelled each other. And then we were able to do electrolysis of copper chloride. We were actually able to move those electrons, take them away from the chlorine by having a battery there, and we were able to produce copper atoms. So that was sort of our basis for beginning this unit. So let's jump right in here to our understanding of electrons now. So electrons, how do you determine the number of electrons in an atom? So I want you to grab your reference table, and right at the top of your periodic table of elements here is this key. So it reminds us that for every element, we can see its electron configuration. So that means, how does it arrange its electrons? What is the arrangement? So as you work out from the center of an atom, there's an energy level with 2 electrons and then an energy level with 4 electrons. So together that totals 6 electrons. So the atomic number right there tells us the number of electrons in an atom. So now that we know that, we can just look up the element's atomic number. Okay, so sodium. And again, if you want to find any element, the table after the periodic table lists each one out, and it's by number. And so sodium is number 11, so that reminds us that it is Na. So sodium has 11 electrons. Titanium has 22. Iron, so I'm finding Fe, and so that has 26. And gold is Au, so it has 79. What is the ground state electron configuration? So ground state is exactly what we saw here. That is my ground state electron configuration. Ground state means, like, what is it normally? Not excited, not as an ion, just what is your normal atom. So everything as listed on the periodic table is for an atom, not an excited atom, not an ion, just a regular ground state atom. So we're going to look up, so this is the normal electron configuration for an atom. So it's the arrangement of the electrons from the center of the atom out. So potassium is element K, so it goes 2, 8, 8, 1. Beryllium is Be, so it's 2-2. Argon is element 18, so it's 2, 8, 8. And again, I'm just looking under the symbol, under the atomic number for the electron configuration. And then chlorine is 2, 8, 7. All right, and then once we understood that arrangement of where they were located, we put a word to it and we said, okay, the outermost electrons were the valence electrons. So if I was looking at each of these here, the valence is the last one. This is the closest to the center of the atom, and this is working its way out. So this is the valence, this is the valence, this is the valence, this is the valence. All right, so for fluorine, let's just look at that last number in its configuration. So its configuration is 2-7, so it has 7 valence. Calcium 2882, so 2 valence electrons. Phosphorus has 5, and aluminum has 3. All right, how do you show electrons? I really just wanted this to say electrons in a Bohr diagram. So Bohr, remember Bohr ring, you need to draw the rings and the electrons. And in a Lewis dot diagram, you do only the valence as dots. And remember, there is a specific order. So let's go over that order again. If this is my element, there's a total of 8 potential valence electrons. So that means that there's spots for 2 of them on each side, since there's 4 sides to this symbol. If there's only 1 valence electron, it would go in this one spot. That is the number 1 spot for a dot for your element. If there are 2, they would occupy these top 2 spaces. If there is a third, we're going to go around the clock like this. This would be the next available spot. The next one is down here at the beginning of this under group of spots. And the next one is over here on the left side. Then we go around again and we say, okay, the next one could go here. The next one could go here, and the last dot here. So for example, we're going to draw fluorine. So the first thing I need to do is look up fluorine's electron configuration, 2-7. So if I did a Bohr diagram, I would write F. I would write the first ring and draw 2 electrons on it. And then the next ring would have 7. And remember, we draw them spaced out because each one is negative, so they don't want to be right next to each other. So I drew the 2 and I drew the 7. When I do the Lewis dot diagram, I write the letter F, and I only need the valence electron, so I need the 7. So that's where the first dot goes, the second dot, the third, the fourth, the fifth, the sixth, and the 7th. So just that one spot is open over here on the left side. All right, let's do the same thing for calcium. Calcium is 2882. Okay, I'm going to go over here because I don't really have a lot of room. 2, 8, 8, 2. And remember, Bohr ring, you have to draw each and every ring and the correct number of electrons that are on each ring. A Lewis dot diagram, now this is why he was my guy. All you need are those outer electrons, because if you think about it, those are the ones that are going to come in contact with other atoms, like bump into them. Literally, if another atom is here, what's it going to bump into? Just the valence. Those are the only ones that it's going to interact with. So 2 dots, the first 2 dots just go on the top. So that's it, 2 dots on calcium. So I'm going to let you go ahead, do the phosphorus, do the aluminum. You can pause the video. All right, and now we're ready for this side. How do ions form? So an ion has a charge. So it forms by either gaining or losing electrons. So those particles here on the outermost part of our atom, so if I was carbon here, these 4, the goal is to get to that octet. 8 is great. That is what will make me stable. So you can either lose electrons to get there or gain electrons to get there. Right here, oxidation states is showing us the most possible choices for each element. So here for carbon, it could be -4. That means it would gain 4 electrons. If it was +2, it would lose 2 electrons. Wouldn't be perfectly stable, but it does that in nature. So that's why they're showing you this is what carbon actually does. Or +4, which means it is going to lose 4 electrons, and then it would be stable. Okay. So metals form. So these form positive ions. They are called cations because they're attracted to the cathode. The cathode is the positive, it attracts the positive, so it is the negative side of the battery, because remember, opposite sides attract. So when you have a cathode to a battery, it's negative and it attracts those cations, those positive ions. So metals do this by losing electrons, and we call that oxidation. So our metals tend to lose electrons and that oxidize. Nonmetals form negative ions called anions because they're attracted to the anode, which is the positive side of a battery. Okay, Lewis dot diagrams of atoms. Oh, this should say ions. Ions, because now we've moved on to ions. So we just did some Lewis dot diagrams of atoms. Now we're going to do ions. They need the electron configuration adjusted. So you're either going to gain or lose. And then they're going to need the brackets, and they're going to need the charges. So I always say A, B, C, D. Make sure you have the atoms, the brackets, the charges, and the dots. So we will go through and show that here. All right, and I'm also going to add that nonmetals, they do what's called reduction. They gain electrons. And I'm just going to show it on the periodic table. All of these metals over here are positive ions. So since these are all positives, they all lose electrons. Here's my staircase. This is what separates all these over here. These are all metals, except you. You're separated. You're a nonmetal. And then everybody over here, you're nonmetals. And you all have negative charges, or at least that top one is a negative charge, which means you gain electrons, because the goal again is to reach that octet. This group is stable. They do not bond. We call them the noble gases. And they have met the octet rule. So if you look, this one only has one shell. So the first shell can only hold 2 electrons. So perfect, it's got its 2. You've got your 8, you've got your 8, you've got your 8, you've got your 8, you've got your 8. So 8 is great, stable. You don't need to gain or lose. You already are stable. So let's go through and do this. So aluminum, look up the configuration first. So Al's configuration is 2-8-3. The atoms Lewis dot diagram would have those 1, 2, 3 dots. Ion, this atom is most likely to form. So I look up in the top right corner and it says +3. So Al with a +3 charge is the ion it's most likely to form. How does it do that? It would lose 3 electrons. So the ion would look like this. Put the bracket on it. No dots because it lost its 3 dots, and put the +3 charge on it. Oh, sorry. I did that in the wrong spot. That has to go over 1. The electron configuration would be 2-8-3. So I cross off the 3, would lose that. So then to show it, I do the AL, I do the brackets, and I do the +3. All right, let's do another one. Fluorine. So fluorine is 2-7. So the atom would look like this. There is a -1 up in that top right corner. That's its oxidation state that is most likely. So it would become -1 by gaining 1 electron. So instead of being 2-7, it would become 2-8. So now when I draw it, I put all 8 dots on. I give it the bracket, and I give it the charge. All right, I'm going to do one more with you, and then you can do the rest. So calcium, 2882, Ca, just the 2 dots. Most likely charge is Ca plus 2. It would do that by losing 2 electrons. So 2A2, lose those ones, which means it has no dots, brackets, and a +2 charge. So each of these are now stable because they've met our octet rule. So go through, do the rest of that practice, pause the video, and restart it when you're ready. Okay, so how can electrons become excited? So to become excited, they need either heat or electricity. We did this when we did our flame lab. So when the excited electron returns to ground state, what does it release? It releases spectra. And spectra, again, was the color of the flame that we saw. How do you notice an excited electron configuration? So it has the correct number of electrons, but an electron has moved out. So it goes to a different shell. So we'll show it here first with lithium. So lithium, again, we're not talking about ions now, we're just talking about the atoms. Lithium is 2-1. So it has 3 electrons total. To be excited, an electron has to move out. So it could be 1-2. So closest to the center of the atom is just 1 electron because now one of them has moved out to the outer ring. All right, 2-7, 7 and 2 adds up to 9. I look up what element 9 is, and that's fluorine. So possible excited could be 2-6-1. It only had 2 rings. Now it could have 3 rings. And we write possible because you also could have said 1-8 because it hasn't filled that ring yet. Okay, 1, 8, and 2. So I add that up and that totals 11. 11 is sodium, Na. Normal for Na, 2-8-1. So go ahead, do the rest of those practice ones, pause the video, and when you're ready, join me down here. So for each, decide if energy is absorbed or released to cause the listed electron movement. So N is the energy level. The closest energy level, 1, is closest to the center of the atom. So if this is the center of the atom, this would be N equals 1. This would be N equals 2. This would be 3, and so on. So if I go from 1 to 2, I am moving out. In order to go out, I have to absorb energy. If I go from 6 to 4, I'd be moving in. When it goes in, that's when it goes from excited back to ground. So that's when it releases energy. This is when you're going to see the color. And so you go ahead, finish those ones. And then bright line spectra is unique to each element, and it appears when an electron returns, sometimes we say falls, from excited state back to ground state. So I'll just draw that for you. So let's say here's my electrons. So I drew 2 and 5. So this is nitrogen. So 2-5, this is ground state. But let's say I have this fire here and it excites this electron and it moves out. Now it would look like this. 2, 4, 1. 2-4-1 is its excited state. So it had to absorb energy in order to move out here to this excited state. But it never stays there. So when this falls back down to here, that's when it releases energy, when it returns to ground. Okay, our next section, types of bonding. So the next thing that we really focused on this unit was learning how atoms come together to form compounds. So we know we have all the elements on the periodic table. How do they come together to make a compound? When electrons are transferred from a metal to a nonmetal, we call that an ionic bond. And the reason why we call that is because we make ions. And then if you have nonmetals, they form what's called a covalent bond. And there's no ions, there's no charges, no crisscrossing. Metals freely pass their electrons, creating a mobile sea of electrons. This creates metallic bonding. So that means metals, they don't transfer their electrons. It's sort of like playing hot potato. They're just constantly passing them back and forth and back and forth. And that's why they're such good conductors of electricity. So for each of the following, we're going to put C if it's covalent, M if it's metallic, and I if it's ionic. So the highest boiling point of these three choices, highest boiling point would mean which one has the strongest attraction. So which one is really held together, the most solid, the most attraction. So that would be a metal. And then ionic would be after that, and the weakest of all would be covalent. Dissolves well in water. Well, metals don't dissolve well in water, but ionics, think salt, ionics definitely do. Covalents do not. And again, it's all about those charges when you dissolve well. Conducts electricity as a solid. So in order to conduct electricity, you got to have mobile charged particles. That metal passing those electrons, even as a solid, will allow it to conduct electricity. If you melt or dissolve in water an ion, then you'll have charges, and then it will be able to conduct electricity. All right, most likely of the three types to be a gas at room temperature. A gas has an extremely low boiling point, which means it has really weak attractions to each other. So the weakest of all of these would be covalent. So think of something like carbon dioxide. That's two nonmetals, so it's covalent bonding, and it's a gas at room temperature. Is made up of positive and negative ions. Ionic bonds have ions. Has luster, is ductile, which means you can make it into a wire, and is malleable. That is a metal. Remember we did the whole lab where we had all those different substances and you had to figure out what type of bonding it was, covalent, metallic, or ionic based on these properties? crystal lattice. So a crystal lattice means it's constantly repeating and its ions are all attracted to each other, forming a crystal. So that's ionic. And then low melting point would have to be our covalent, because they're weak attractions. So to conduct electricity, so I want to add that word in here, electrolyte. Electrolyte is a solution that's able to conduct electricity. So to conduct electricity, a substance must have, here's the rule, you got to have mobile charged particles. So a mobile charged particle could be an electron or it could be an ion, because they both have charges and they both have the potential to be moving. If you have an ionic solid, they're not moving yet. To be mobile, they got to be moving. So you have to either make them into a liquid or you have to dissolve them. So as a solid, only metals conduct electricity. Ions become mobile when a solid is melted. So liquid compounds, oh, ionic, sorry, I see. Sometimes I wonder what I wanted for fill in the blanks. There it is, I wanted ionic. Liquid ionic compounds do conduct electricity. If you dissolve an ionic compound in water, it has mobile ions. That was our goal. So it does conduct electricity, or so it can conduct electricity. And then covalent compounds have no ions, so they do not conduct electricity. Or you could also say that they're just poor conductors, because if one of them could conduct a little tiny bit, it would be very poor. All right, writing formulas and names. So we did spend a lot of time this unit working on naming and writing formulas. So if we have a covalent molecule, then it is made up of only nonmetals. There's no ions, which means there's no charges. No ions, no charges, so no crisscrossing. The name tells you the formula because it has the prefixes in it. And again, I always think it's easiest if you have an example right in your head. Covalent, right away you think of something like carbon dioxide. There, you just said the name and you said it with prefixes. So it reminds you, the prefixes tell you how to write the formula. Ionic is made up of a metal and a nonmetal. The metal is going to lose an electron. The nonmetal will gain that electron, or 2 electrons, or 3. You crisscross the ions to get your formula. If the metal has more than one possible oxidation state, so more than one possible charge up there in the top right corner, like let's say it could be a +2 or a +3, then you need to give it a middle name. The middle name is equal to the charge in Roman numerals. So for example, if I wanted that 3, I would give it the middle name 3. Okay, if they have both, then they must contain an ion from table E. So here's table E. These are our polyatomic ions. So multiple atoms forming ions. So all of these have a charge. They also have names. You do not change the names. You also do not change that formula. If it's CrO4, don't even think about changing that 4. If you need 2 CrO4s, you would just put it in parentheses and say you need 2 of them. But do not change the charge or the number. Okay, there it is. Do not change the formulas or names on table E. Crisscross charges to get the formula. If you need multiples, you must use parentheses. If the metal has blank, you need to show the charge of the metal using Roman numerals. So if it has more than one possible charge, just like ionic, you have to do the same thing if it has both. Okay, So the first thing we always do when we're practicing is we figure out the type of bond so that we know how to name it. So an O and a Cl are both nonmetals. So that means that it is covalent. That means I'm going to name it with prefixes. So I write oxygen and then 2Cl. So that's dichloride. All right, this one they gave me the name. Nickel 2 nitrite. Weird name. That weird name tells me it's on table E. That tells me it has both. And to write the name, I don't have a lot of room here, but let's see what I could do. Ni with a +2 charge. So that's the first thing I want to do. Ni with a +2. Then I got to look up nitrite. There it is. Not ate. So I want NO2 with a minus. I crisscross those charges. So I get Ni, just one of them. Sorry, I'm not sure why I'm getting that. Let me erase this, give myself a little more room. Okay, 1 Ni. And then I need 2 NO2s. So I'm going to put NO2 in parentheses and a 2 after it. So that's showing I need 2 NO2s. Okay, next one, Mn. I don't know why I keep getting those black lines. Go away. All right, Mn. So Mn is manganese. So I can write that right away. And S is sulfur. So I have just ionic. I don't have anything from table E. I just have an ionic. And the 3 came from the Mn. The 2 came from the sulfur. So let me draw that out a little bit better. Mn was the +3. S was a -2. I'm just reversing those numbers so I see what the charges were. Manganese, Mn, has 1, 2, 3, 4 possible oxidation states. So I have to show in the name that it was a +3 charge by putting a 3 in Roman numerals. And then sulfur, I write sulfide. Okay, so you're going to go through, do the rest of this practice. And I'm going to stop this video, and when you are ready, you are going to start the next video of Unit 6 review. Make sure you're writing down questions that you have for me so you can ask me in class.